Hi everyone, welcome back to my channel. Today we are going to discuss a very important algorithm called momentum based gradient descent algorithm. In previous video, we have understood the classical gradient descents and its limitations. Today we are going to discuss the improvement of the limitation of the classical gradient descent with this new approach. The main idea behind momentum is very intuitive. A classical gradient descent, every update depends mainly on the current gradient. Because of this, the optimizer can sometimes take small zigzag steps, especially when the direction of the gradient keeps changing. Momentum tries to solve this problem by remembering the previous direction of the movement. Think about a ball rolling down a slope. As the ball moves downhill, it gains momentum. If the slope continues in roughly the same direction, the ball does not stop and restart at every point. Instead, its previous movement helps it continue forward. Momentum-based gradient descent works with similar intuition. If the optimizer is repeatedly being pushed in the same direction, we can gain confidence in that direction and gradually take larger and smoother steps. Look at the blue trajectory in the figure. This represents momentum-based gradient descent compared with the gray trajectory of the vanilla gradient descent. The momentum path is smoother and tend to move more efficiently toward the minimum. The gray path shows the behavior of the classical gradient descent where the optimizer can make smaller and sometimes zigzag movement. The blue path, on the other hand, uses information from the previous updates to maintain movement in the consistent direction. So, the momentum has two important effects. First, it accelerates movement in a consistent direction, and second, it reduces unnecessary oscillation or zigzag movement. As a result, momentum-based gradient descent can often reach the minimum faster and a smoother optimization path. So instead of looking only at where the gradient is pointing right now, sometimes a momentum also considers where we have been moving previously. And this simple idea gives gradient descent a kind of memory. In the next few steps, we will look at how the momentum is mathematically incorporated in the descent parameter update. Continuing from the previous slide, we saw the basic intuition behind momentum-based gradient descent. We said that momentum gives the optimizer a kind of memory. Instead of relying on the current gradient, it also uses the direction of previous updates. Now let us visualize this idea on a two-dimensional loss surface. The surface shown here represents our cost function with two parameters theta and theta1 and theta2. The lowest point of the surface is the minimum, which is our optimization target. We start from the point marked start and the read point show the successive parameter updates during training. Notice how the optimizer moves down the surface toward the minimum. The important thing to observe that the momentum uses the previous update direction to build speed. So when the several consecutive gradients point in a similar direction, their effect accumulates. The optimizer gain momentum and take larger steps in that consistent directions. This is why the momentum path can move more smoothly towards the minimum instead of making a small inefficient movement. Compare this with the vanilla gradient descent path shown in the gray. Without momentum, the optimizer reacts directly to the current gradient. This can produce more oscillation, especially when the loss surface has different slope in different direction. Momentum helps reduce the unnecessary oscillation and maintains a movement towards the minimum. So the main goal is not simply to make step larger. The goal is to make the movement more informed, smoother, and faster by carrying information from the previous updates. Therefore, as shown in the figure, momentum can help gradient descent reach the minimum faster with fewer oscillation. And now that you understood the intuition, the next slide we can look into mathematical update equations of momentum based gradient descent and see exactly how memory of the previous updates is incorporated. Continuing from the previous slide, we have seen visually how momentum helps gradient descent move more smoothly and reach the minimum faster. Now let us understand how this momentum is actually introduced mathematically. The slide shows the update rule for momentum-based gradient descent. The first equation defines the update at iteration t. It says update t equals gamma multiplied by update t minus 1 plus eta multiplied by the gradient of w at time t. Let us understand each part of this equation. First term is a gamma multiplied by update t minus 1, where update t minus 1 represents the update from the previous iteration. So we are carrying some information about the previous movement into the current update, and the gamma is called the momentum coefficient. As shown on the slide, gamma lies between 0 to 1. If gamma is larger, more information from the previous update is retained. If gamma is smaller, the influence of the previous updates is reduced. The second term is eta multiplied by the gradient of w at time t. Here, eta is the learning rate, which controls how strongly the current gradient influences the update, and the gradient of w at time t represents the direction and the magnitude of the current gradient. So the current update is actually a combination of two pieces of information. The previous update controlled by the gamma and the current gradient controlled by the learning rate eta. This is the key behind the momentum, where we're not starting every iteration from scratch. Instead, the optimizer carries forward some information from its previous movement. Once this update has been calculated, the second equation tells us how to update the actual parameter. It says Wt plus 1 equals Wt minus update t. In other words, we take the current parameter Wt and subtract the newly calculated update. So the overall process is first calculate the momentum based update using previous update and the current gradient. Then we use that update to obtain the new parameter value. This is exactly how the optimizer develops the momentum or memory that we discussed in the previous slides. And now we can clearly see the connection between the intuition and the mathematics. The previous update provides momentum, while the current gradient provides the new direction. Now that we have introduced the momentum-based update rule, let us break it down step by step and see exactly how the previous update influences the current update. We start with the initial condition. At the beginning, we assume that the update 0 is equal to 0. This simply means that before the first iteration, we have no previous update information available. Now let us calculate the first update. The equation say update 1 equals gamma multiplied by update 0 plus eta multiplied by the gradient w1. Since update 0 is equal to 0, the first term disappears. Therefore, update 1 equals to eta multiplied by the gradient w1. So during the first iteration, there is no momentum contribution yet. The optimizer uses only the current gradient. Now let us move to the second iteration. The update rule becomes update 2 equals gamma multiplied by update 1 plus eta multiplied by gradient w2. We already know that the update 1 is eta multiplied by gradient of w1. So when we substitute it into the equation, we get update 2 equals gamma multiplied by eta multiplied by gradient w1 plus eta multiplied by gradient w2. Now notice something important. The current gradient, which is the gradient of w2, gets its full contribution. But the previous gradient, which is the gradient w1, is still present and the contribution is multiplied by gamma. This is the first sign of momentum. the optimizer is not forgetting the previous direction completely. Instead, it carries part of that previous information into the current update. So, after just two iterations, the update already contains information from both the current gradient and the previous gradient. If we continue this process for more iterations, something very interesting happens. The update will start containing not just the two gradient, but the entire history of the previous. We have already seen that the second update contains information from both the first and the second gradient. Now let us continue the same expansion for the third and fourth update. For the third iteration, the update is update 3 equals gamma multiplied by update 2 plus eta multiplied by the gradient of W3. From the previous slide, we know the update 2 contains the first and the second gradient. So when you substitute update 2 into this equation, we obtain update 3 equals gamma squared multiplied by eta multiplied by the gradient 1 plus gamma multiplied by eta multiplied by gradient of 2 plus eta multiplied by the gradient of W3. Now look carefully at the coefficients. The most recent gradient, the gradient of W3, has the coefficient of eta. The previous gradient, the gradient of W2, has a coefficient of gamma times eta. And the older gradient, the gradient of W1, has coefficient of gamma squared times eta. So the older gradient becomes the higher power of the gamma becomes. Let us continue one more step. For the fourth update, we get update 4 equals gamma cube times eta times the gradient of W1 plus gamma squared times eta times the gradient of W2 plus gamma times eta times the gradient of W3 plus eta times the gradient of W4. Now the pattern is very clear. The newest gradient received the largest weight. The previous gradient receives slightly smaller weight, and the older gradient receives progressively smaller weights because they are multiplied by the higher power of gamma. So the momentum is effectively keeping a history of the previous gradient, but it does not give equal importance to all of them. Recent gradients receives more importance, while older gradients gradually lose their influence. This is why the slide uh, describes momentum as exponentially weighted average or EWA. In general, the update at time t can be understood as a weighted combination of current gradient and all previous gradients. The weights decrease exponentially as we move further into the past. For example, the most recent gradient is multiplied by eta. The previous one is multiplied by gamma times eta, and the one before that multiplied by square times eta, and the pattern continues. So if the gamma is between 0 and 1, higher power of the gamma become progressively smaller. This means that very old gradients have less influence on the current update, while recent gradient retain stronger influence. And this gives us very useful interpretation of the momentum. Momentum is not only simply making the learning rate larger, instead it creating a kind of memory of previous gradients where recent history is remembered more strongly and older history. This explains the behavior we saw in the earlier visualization. When several consecutive gradient points in a similar direction, their contribution accumulate through this weighted history. The optimizer gains momentum and moves faster in that direction. At the same time, rapidly changing direction are partially smoothed out. So the mathematical expansion we have derived here explains the intuition we discussed earlier. Momentum accelerates consistent movement and reduces the unnecessary oscillation. Now that we have understood how momentum works and why it can accelerate gradient descent, let us also look at its limitations. Momentum keeps optimizer a kind of memory. As we discussed in the previous slides, this memory helps accumulate movement in a consistent direction. But this same property can sometimes become a problem. Look at the top graph. The red dashed line represents the optimal point, which is around 0. The blue curve shows how the parameter changes over successive iteration. Notice that the parameter does not move directly to the moment optimum. Instead, it moves from one side to the other, repeatedly crossing the optimal point. This happens because the accumulated momentum can carry the optimization process beyond the momentum. In other words, even after reaching the neighborhood of the optimum, the optimizer may still have enough momentum to continue moving forward. So the first limitation is overshooting. Momentum can move the optimization beyond the optimum point. Now notice that what happens over the iterations. The oscillation gradually becomes smaller, but the optimizer continues moving back and forth around the minimum. This is the second important limitation. Because the momentum accumulates previous updates, it can sometimes carry the optimization across the valley of the loss function. As a result, optimizer may oscillate from one side of the minimum to the other before finally settling down. The bottom graph gives us another view of the same behavior. Here the rate points and the trajectory shows the path taken by the momentum-based gradient descent toward the minimum of the loss function. We can see that the optimizer approaches the minimum efficiently, but there are still small oscillations around the optimal point. However, there is an important positive point. Even though momentum can introduce this oscillation, it usually converges faster than vanilla gradient descent. So momentum provides a useful trade-off. It can accelerate optimization and reduce slow zigzag movement, but if the momentum is too strong, it can cause overshooting and oscillation. This means that momentum coefficients and the learning rate need to be chosen carefully. And this limitation motivates us to look for another approach, one that can automatically adjust the size of the update of different parameters.